Hi everyone, this is your first YouTube lecture on Chapter 1 in the Ch1 chemistry book. And this focuses on matter, the states, classifications, and properties of matter. So we've already talked about chemistry is the study of matter and the changes it undergoes. And we've gone over these quick definitions in class today, but matter is anything that takes up space and has mass. And I gave the kind of tricky definition of a pure substance, or often just called a substance in chemistry. It's a form of matter that is definite composition and distinct properties. So these can be elements like nitrogen or gold or silicon, compounds like sodium chloride and sucrose, which have definite compositions of more than one element. A mixture is a combination of two or more pure substances where those substances retain their identities. There's two kinds of mixtures. A homogeneous mixture. In a homogeneous mixture, the composition of the mixture is the same throughout. And this kind of brings up an interesting point that I'll get into on the next slide. But one example of a homogeneous mixture is a solution. A solution is something, and you would typically think of a liquid, where a solid substance is dissolved in a solvent, and those ions or molecules are 100% completely evenly distributed throughout the solvent. In a heterogeneous mixture, the composition is not uniform throughout. So a couple examples here. A soda would be an example of a heterogeneous mixture because you've got little air bubbles. Those air bubbles are different from the rest of the material in question. Another example that would be pretty obvious would be a mixture of iron filings and sand. But this question often brings up some finer points. The biggest question I always had when taught about homogeneous mixtures is at what level do they need to be homogeneous at? Is it the atomic level, or is it to the naked eye, or the level of a microscope? Take for example milk. When we look at milk with our eyes, it looks very homogeneous. It's white, and one little bit here is the same as one little bit there. But if we start zooming in on a sample of milk, if we magnify it 400 times, we start seeing little specks, and the specks in this microscope image are fat globules. So you don't have just one fat molecule in solution. Fats tend to stick together, and they like each other. They're hydrophobic, so they stick together, and they make these globules consisting of many molecules of fat. To look at a rendition of what this looks like at an even smaller level, you can see that zooming way in, there's very clear areas of fat versus the serum of the milk. And in this picture, this is from a bacteriology textbook, you might even have bacteria in there, which throws in a whole nother wrench. Things that you can't see could potentially make a mixture heterogeneous. So this is often a loaded question, and in class I'm going to ask you for your homework, to defend both sides. I might give you a substance and say, explain how you might consider it heterogeneous, explain how you might consider it homogeneous. Okay, so now moving on to the pure substances again. A compound is a substance composed of atoms of two or more elements. And these are chemically bonded together, chemically united, and they're always in fixed proportions. So the picture here, the mineral quartz. Quartz is SiO2, silicon, one atom of silicon and two atoms of oxygen. It's always in that ratio. And most rocks are composed of varying compounds or minerals. To separate the silicon from the oxygen, or lithium from fluoride, you can only accomplish that by chemical means, by chemical reaction. And sometimes that reaction is pretty cool. I wanted to bring up a quick YouTube clip of a chemical reaction. This is the decomposition of mercury thiocyanate. And the mercury thiocyanate is a ordinary looking white powder, but when it's ignited, it goes through a fairly complex reaction actually, in which some of the elements that make up that compound break down, and nitrogen gas is released. There's kind of a whole bunch of stuff made, but also elemental mercury is often produced. And it's not the bulk of this weird formation that's growing out of this powder, but it often coats, it often vaporizes, and some residual coats that stuff. So that's one example of a decomposition reaction in which the elements can be isolated out of that compound. With a mixture, you can separate out the components by physical means. So one common laboratory technique is distillation, where you could have a solution, maybe containing alcohols and waters, and separate out all of those compounds that are in there. Another fairly simple separation technique with that example of iron filings and sand is that you could use a magnet to pull out all those magnetic iron filings. An element is a substance that can't be separated into simpler substances by any chemical means. And so this is our very basic unit that we will talk about a lot in chemistry. There's 82 elements naturally occurring on Earth, including gold, aluminum, lead, oxygen, and some pictures of a few of these elements. And then there's 32 elements that have been created by scientists, including technetium, americium, seaborgium. These are all elements that have been created in nuclear processes. Now, I didn't mention that first bullet point because these slides are now a little bit dated as of a couple weeks ago. Scientists have recently identified element 115. There's not a lot known about these man-made elements are typically not very stable. So there's not a sample of element 115 just that you can just order from a chemical supply company. But it does have some pretty interesting properties. You can see the periodic table here. We'll talk about this in a lot more detail later on in the course. But the element 115 has some pretty interesting properties in that it may be more stable than some of these super heavy elements that have previously been produced by chemists and physicists. So just to recap, matter can be classified as into really two main classifications: mixtures or substances, pure substances. And underneath mixtures, mixtures can be either homogeneous or heterogeneous, and substances are either compounds or elements. Now, oftentimes when people think about the classifications of matter, you might think, oh, solid, liquid, or gas. Technically, we call that the states of matter. A substance is either in a solid or a liquid or a gaseous state. And you've probably seen a graphic like this before. In a solid, the building blocks of that substance, the molecules or the ions or the atoms, are they're in some sort of lattice, or maybe fairly amorphous. It might not be as structured as this picture indicates, but they're very, very tightly packed together. In a liquid, they're also tightly packed, but they're able to slip past each other, and that's what gives rise to the fluidity of liquids. And in a gas, they're much less dense. They're very much spread out, occurring only, and they take up much more space than the same compound or element in a liquid or solid state. Just a quick example of that: if you take a big block of ice and put a hot piece of metal on it, you're going to kind of disrupt the crystal structure of the ice, which you can see in this image of the cartoon of the solid ice. And you'll get some liquid right at that surface, and then some of the molecules will escape into the gaseous state. So let's talk about how we change matter. A physical change doesn't alter the composition or identity of a substance. So some examples of that are ice melting, the ice in the water. You've all eaten ice cubes before. It tastes like water. Sugar dissolving in water. also the sugar still tastes like sugar. Chemical change is really synonymous with a chemical reaction. And in a chemical reaction, you've got a whole new substance resulting from that reaction. So when hydrogen burns in the air, it forms water. And that's it for our first YouTube lecture.